And I'm Carola.
And welcome to our very first video in a new series of computational geometry concept videos. And in these videos we take a geometric concept and dive into its definition, history, complexity and other interesting properties.
So why are you making these videos?
Well, as humans have known for as long as there are written records, geometry is everywhere. And nowadays computers are everywhere too, and computers deal with geometric problems all the time.
Yeah, so in this series is meant for anybody who would like to know a little bit more about how computers do that exactly. So there's going to be a little bit of mathematics, there will be some proofs, but also if you don't know anything about math, we hope that you'll learn something from these videos.
So what is the concept of today?
Well, today's concept, our very first concept, is the closest and furthest pairs.
This is a live oak. Live oaks are iconic landmarks across much of the southern United States, and they're an essential part of the scenery of New Orleans, such as here in Audubon Park. Now this is another live oak. And these two particular trees are a little bit close to each other. The LSU Ag Center advises that live oaks be spaced at least 60 feet away from each other and ideally even 90 feet in order to give them enough room to grow. There are about 150 live oaks in this park. So now suppose you know the locations of every single tree in the park, or in the city, or even in a bigger area. Then how would you find the closest pair, or similarly, the farthest pair?
The definition of the closest and farthest pair is actually fairly simple. We're giving a set of sites, let's call it S, and let's say they live in two-dimensional Euclidean space.
So this is named after Euclid of Alexandria,
an ancient Greek mathematician who's famous for his book The Elements, which he wrote about 300 BC.
Very important book. It forms the basis for what we know about geometry and actually much of mathematics as we use it today.
It gives a mathematical model of the plane the way we know it.
So we live in a three-dimensional space, two-dimensional space is like one slice of it, and within that space we can do things like measure distances. Such as measuring distance between trees. So these trees are 16 feet apart.
And let's forget about like 3 dimensions and curvature and such. And let's say we have n such sites. Then for each pair of sites we have the distance between them, which is just the Euclidean distance, the distance you would measure with a ruler. And we will denote the distance with vertical bars like this. Now the closest pair is the set of sites in S such that their distance equals the minimum distance over all pairs of points in S. The closest pair is the pair CD such that the distance between CD is the minimum over all pairs of sites A, B, and S, with A not equal to B, over the distance AB. Similarly, the farthest pair is the pair whose distance equals the maximum of all distances among all pairs of points in S. The farthest pair is the pair EF, such that the distance between E and F is the maximum over all pairs AB and S with A not equal to B, such that over their distance AB.
This simple definition, of course, gives an easy way to calculate the closest and the farthest pair. We can just compute the distance between each pair of points, write all these distances in a big list, and then take the minimum and the maximum from that list. So that works, that's a working procedure, and it will give us the correct answer. And a procedure like this is what we call an algorithm. However, a potential problem with this algorithm is that the length of that list scales quadratically with the number of points or sites. So for example, if we have only 10 sites, then the number of pairs is, well, 10 times 10 minus 10 because a site with itself is not a pair, and divided by 2 because every pair occurs twice, so that's 45 pairs. That's not too bad. But if we have 100 sites, then the number of pairs is already 4,950. Now, whether that is a problem or not really depends on the situation. So it depends on the number of sites we actually have, but it also depends on how much time we have, how fast we need the answer, and of course how fast the computer is that we are going to use to compute the answer. But independent of all that, there is a fundamental algorithmic question here, and that's, can we do this faster? So is it possible to design a procedure, an algorithm, to compute the closest or farthest pair among a set of sites that doesn't scale quadratically with the number of sites? The problem of computing the closest pair is a little bit trickier than it might seem at first sight.
You know, I mean, intuitively, it shouldn't be that hard for one site to sort of just look at sites that are close to it, right?
Yeah, I mean, it's kind of a human way of looking at it. So things that are close to each other, you see them at the same time, but that's not how computers work. So for computers, it's a little bit different.
So in 1976, Michael Rabin designed a randomized algorithm.
Randomized is, well, the way the algorithm works is random. So it doesn't. When you run the same algorithm multiple times, then it could take longer one time than the other time.
A randomized algorithm to compute the closest pair between n sites, where the expectation of the amount of time it takes the algorithm to compute the pair is linear in the number of sites.
Right, so linear means that if you have twice as many sites, then it takes twice as much time. So the way it scales is linear.
In 1979, John Hopcroft and Steve Fortune were able to develop a non-randomized algorithm at the expense that it takes n log n time.
Yeah, so the logarithm of the logarithm, so it's actually, I mean, it's not constant, but in practice it's so small that it's almost as good as linear. So the logarithm of the logarithm of 1 million is around 5.
And the logarithm of 1 trillion is about 6.
Right.
In 1983, Ken Clarkson.
Clarkson had a paper in 83 where he showed you can do it in n log n time.
Exactly. So the earlier papers assumed that the numbers that are used to store the coordinates of the points of our sites can be stored in a fixed number of bits.
Mm-hmm. Right, yeah. So computers use bits to store data, so every number is a sequence of bits.
Clarkson showed that that's not necessary. So Clarkson actually showed, so actually at the expense of having an algorithm that runs in n log n time, he showed that you can do this even when the numbers that are used to store the coordinates are actually real numbers.
Real numbers are really just numbers as we think of them every day. So we could draw a number line. And this line contains all possible numbers. So for example, 0 is a number, 1 is also a number, -1 is a number. But all of these numbers are actually what we call integer numbers. And the real numbers contain also all the numbers which are not integers. So for example, 1/2 would be a number which is not an integer. And square root of 2 is also a number, but not an integer. So all of these numbers together are also denoted by this R with a double stem. That's the set of all possible real numbers. So why do we call them real numbers? Well, that's because mathematicians also invented something called imaginary numbers, which are not real. But you don't have to worry about those. All of the numbers in this video series will be real. And not every real number can be described by a finite sequence of bits, so there's a discrepancy there.
So if a computer could actually work with real numbers, then the closest pair can be computed in n log n time, which is still almost linear.
Yes,
so
it's still much faster than comparing every pair, which would be a quadratic number.
The way Clarkson computed the closest pair is by first computing the minimum spanning tree, or MST, of the sites. The minimum spanning tree is the cheapest way to connect all the sites. Once we have the minimum spanning tree, we can make a crucial observation. The two sites CD forming the closest pair must be connected in the minimum spanning tree. Why? Well, imagine this was the MST and CD were not connected. Then we could add that connection to the minimum spanning tree, like this, which would of course make the total length longer and would also create a cycle. So then it's actually not a tree anymore. So then we could remove another edge of the cycle, let's say this one here, but now AD must be longer than CD because AD was apparently not the closest pair. Now we removed an edge that was longer than the closest pair, so then we would get a tree with an overall shorter distance, which can't happen because it was supposed to be the minimum spanning tree to begin with. So that overall can't happen. Okay? So then we know that the closest pair is directly connected in the minimum spanning tree. So when we have the minimum spanning tree of n sites, it has n-1 edges. So all we need to do is check all the edges and compute the minimum, the one with the smallest distance. So that takes linear time. Of course, we assumed here that we have the minimum spanning tree given. So then the question is, how do we compute a minimum spanning tree and how long does it take? Well, that's the topic of a whole other video. Well, the farthest pair has a very different nature than the closest pair.
Yeah, also deceptively simple. It feels like it should be easy to find the farthest pair, and in fact, there are several published papers in the literature that claim an algorithm to find the farthest pair, which turned out to be incorrect.
Exactly right. Yeah. So that was in the early 80s, and they claimed to have algorithms that run in the order of n log n time, and those were published papers, and neither the authors nor the reviewers found the mistake. The reason for these incorrect algorithms is that they rely on assumptions that appear natural, but upon closer study turn out to not always be true. In this case, consider the following claim. If A is the farthest point from B, and B is the farthest point from A, then A and B form the farthest pair. Seems reasonable, right? It's not always true though. We could have 2 points A and B that are each other's farthest point, but 2 different points, C, D, are closer to both A and B, but not to each other.
Science is still the work of humans.
And that's why it's good to have a peer review process, but it's still the work of humans. So.
Right.
But there was also a correct algorithm, actually.
Right, yes.
Right.
The one by, was it by Seamus?
Yes, by Seamus, exactly. In his PhD thesis from 1979.
Godfrey Toussaint wrote about it later. Maybe I have that actually. Yeah, this one.
Oh, wait, when was that? Ah, the 83, right.
Right. It's solving problems with the rotating calipers. Kind of iconic.
I know. Yeah, in fact, most of these efficient algorithms for solving the farthest pair and also the closest pair, they rely on using some other geometric structure. So this one here uses the convex hull.
The convex hull of a set of sides is those sides that are somehow not surrounded by other sides, so the sides that are on the outside. So another way to see it is that the convex hull of a set of sides is the smallest convex curve that surrounds all of the sides. So, for example, if I release a rubber band around a set of pins, it's going to take the shape of the convex hull. So intuitively, it makes sense to restrict our attention to only those sides which are on the convex hull, right? Because the farthest pair probably doesn't use any side that is surrounded by other sides. However, is this really true? If you remember our earlier claim, which sounded reasonable but turned out to be false, we really should prove claims like this. So we should prove that the two sides forming the farthest pair are actually both on the convex hull. So how do we prove this? Well, consider any set of sides and let's say that the farthest pair is formed by two sides A and B. Now consider the line through A that is perpendicular to AB. So now I'm claiming that all the other sides must be on the same side of this line as where B is, so on the right in this picture. So the sides could be somewhere here, but there cannot be any sides over there. So why is that? Well, if there would be any side on the other side of this line as B is, then the distance from that side to B would be longer than the distance from A to B. All of the points that have the same distance as A to B form exactly a circle. And this circle is contained exactly on one side of this line. Alright, so now if there are no sides on the other side of the line than B is, then, well, by definition that means A must be on the convex hull. And by using a symmetric argument, we can also argue that B is on the convex hull. So, now we have proven that we only need to consider those sides which are on the convex hull and we can safely discard all the others. Alright, so how do we use the convex hull to find the pair of sides that form the farthest pair? Well, for this we can use a clever idea that's called rotating calipers. So for this we take two long elongated objects that are the same length and that are parallel, and we'll keep them parallel. And what we do is we move them towards each other until they touch our sides, or the convex hull. And now my claim is that this pair of points, A and D, is a candidate for the furthest pair. In fact, A and D are the furthest pair in this direction. However, maybe this is the wrong direction and maybe I should have picked a different direction. Well, this is where the rotating part of rotating calipers comes in. So now the trick is that we start rotating these two objects while keeping them parallel. And as we rotate them, eventually one of them will hit another side. Okay, so now I'm hitting A and C. And so AC is another candidate pair for the farthest pair. And we just keep doing this. So we keep rotating until we hit another side, and there we have another side. So now we have G and C that are both touching my rotating calipers. And now we just keep going until we rotate all the way around and we're back where we started. we've rotated 180 degrees and we found a list of potential farthest pairs. Right, now I'm making two different claims. So the first claim I want to make is that during this rotation process I actually only found a linear number of candidate pairs. And the second thing I want to claim is that among this linear number of pairs I actually found the farthest pair. So one of these pairs is the farthest pair that we're looking for. And in fact, in this example, the farthest pair would be given by CF. And indeed, CF is in the list. Try to think about these claims and see if you can prove them for yourself. Alright, so are we now done? Well, sort of, but just like with the minimum spanning tree before, we did make an assumption here, and the assumption is that we have the convex hull of our sites. Alright, but how can we compute the convex hull and how long does that take? Well, that's another story for another video.
Alright, so to find out some basic statistics about these trees, we either have to spend quadratic time in the number of trees in the park, or we'll just have to learn about some more geometric concepts.
Alright, you made it to the end of our first computational geometry concepts video. Congratulations! We hope you enjoyed it and learned something.
Yes, and what we've learned is that both the closest and the farthest pair of sites can be computed easily in quadratic time, but also that both of them can be computed much faster by utilizing different geometric concepts, in particular the minimum spanning tree and the convex hull.
Yep, so we will have other videos about more computational geometry concepts, and if you have questions about more details, we've posted our sources and more details in the description below.
Right. Thanks for watching.